Welcome to Lecture 3 of the Computer Application for Bioproducts and Biosystems Engineering course. In this week's lecture, we will talk about solving equation set systems using linear algebra. We will introduce the equation set by going to an engineering problem in the bungee jumping example. Then we will talk about how to format the engineering problem to a linear algebra problem. We will explore the matrix operation rules that are useful in solving these problems. And then we introduce one basic method called Gauss elimination and its application using MATLAB. In the end, we will talk about LU factorization and its application using MATLAB. Suppose that 3 jumpers are connected by bungee cords, and we are asked to compute the displacement of each of the jumpers. In the unstretched situation, which is shown in the picture A, each cord fully extended but unstretched, and we can define 3 distances, x1, x2, and x3, as measured downward from each of their unstretched positions. And after they are released, gravity takes hold and the jumper will eventually come to the equilibrium positions shown in B. If we assume that each cord behaves as a spring and follows Hooke's law. Okay, I will start over this slide. Suppose that 3 jumpers are connected by bungee cords, and we are asked to compute the displacement of each of the jumpers. So in situation A, where it shows each cord fully extended but unstretched, we can define 3 distances, x1, x2, and x3, as measured downward from each of their unstretched positions. And in situation B, which is after they are released, gravity takes hold and the jumpers will eventually come to the equilibrium position shown in B. If we assume that each cord behaves as a spring and follows the Hooke's law, then free body diagrams can be developed for each jumper as depicted in the right figure. Jumper 1 has 2 cords attached to him, one pulling him up and one pulling him down. Let's use K1 as the spring constant of the cord pulling him up, and K2 as the spring constant of the cord pulling him down. And similarly, K3 will be the spring constant pulling the middle jumper down. And this third cord is also pulling the bottom jumper up. In Newton's second law, force balances can be rewritten for each jumper, and we get these following 3 equations, where M1, M2, M3 are the mass of the jumper, and K1, K2, K3 are the spring constant for cords, and X1, X2, X3 are the displacement of jumpers, which are our unknown values. And we can come up with steady state solution where x1, x2, and x3 are the unknown, and we already know k1, k2, k3, and m1, m2, m3, and g from the previous slide. So we can rewrite the equation set to this matrix format.